Hey there, we're going to go over some simple harmonic motion notes. And simple harmonic motion, it's really described as oscillatory motion. And oscillatory motion is just motion that repeats itself at a regular time interval. Okay, so that motion repeats itself at a regular time interval. Now, in order for an object in motion to be considered simple harmonic motion, one has to be moving with this oscillatory motion back and forth, but we also have what's called a restoring force. And a restoring force, it's really just a force that causes an object to move back towards its equilibrium position. So it causes the object that's in motion to return to equilibrium position. So when we say simple harmonic motion, what we're referring to is an object that's moving in this oscillatory motion where it's moving back and forth at a regular time interval, and there's some kind of restoring force that's causing that object to return to that initial equilibrium position. And for our class, we're really going to look at two different types of objects that move with this simple harmonic motion. And the first one is a mass on a spring. Now, this can be one of two types. Okay, we could have a vertical spring, and a vertical spring would look something like this, where I have a spring that's attached to some kind of rod, and it's hanging vertically. And then there's some kind of a mass that's attached to it. And then we could pull that mass down and stretch it out, so it looks something like this. And then when we release it, that spring is going to start moving back up. So there's a restoring force that calls from the spring, causing it to move back up towards our equilibrium position. So it would look like this. And it's going to keep moving, and it's going to start compressing the spring. So then it would look something like this. And then my restoring force, my force calls from my spring, will cause it to move back towards your equilibrium position. And then we would just continue to repeat itself. Now, one thing to note here, at this location right here, this is my x naught, that's my equilibrium position. And right here, the distance from here to here, that's your stretch. Remember Hooke's law, where we used Hooke's law and we had to measure that stretch there. And so up here, at this one, from here to here, this is also your stretch. So this is a vertical spring. We could also have a horizontal spring. And a horizontal spring would basically be the same thing, except for it's on some kind of a horizontal surface. So if I drew a table, let's say this is your lab table, and I have a spring that's kind of fixed to this wall here, and then the spring is now horizontal attached to a mass. And so this time with the horizontal spring, it's just going to be moving side to side versus up here where it was moving up and down. So if I drew the spring at the different locations here, so let's just draw the mass and not the spring. This could be your max stretch right here. This would be my equilibrium position. and then your max compression would be over here, and it's going to go back and forth side to side. So this is the first type, a mass on a spring, of this simple harmonic motion. The other is going to be a simple pendulum. And a pendulum would look something like this. So I have a string, let's say it's fixed to something and it's hanging down, and then I have a ball that's attached to the spring. And if we pull this ball, say to right here, and then we let go, it's going to start swinging back and forth like this. Now my restoring force here this time is going to be gravity, right? Because whenever I'm in this position right here, that gravitational force is going to cause it to move back towards your equilibrium position, which is right here. This would be your equilibrium position. And it's going to swing back and forth. Now the difference between these two is we have a spring here, and my restoring force is going to be the spring, whereas over here your restoring force is going to be gravity, the force of gravity. So these are the two basic types of objects that move with this simple harmonic motion that we're going to be looking at throughout this unit. Now there's a couple of vocabulary terms you need to be familiar with. One of them is period. Now we kind of talked about this during our circular motion unit. If you remember, the period was the time for one revolution, right, for the circle. So it's very similar here with this oscillatory motion. The period is going to be the time for one full oscillation. And again, we're going to use that capital T that represents the period. Another new term that you need to be familiar with is frequency. Now, a lot of times frequency and period, they're kind of mixed up. Frequency, it's just the number of oscillations per second. So it's the number of oscillations per second. And we use a lowercase f to represent frequency. So frequency, number of oscillations per second, period is the time for one oscillation. And we actually have an equation that kind of relates these two together. So capital T period is equal to 1 over frequency. So if you know the frequency, then you can solve for the period. Just do 1 divided by your frequency. Frequency is also measured in hertz, so Hz. Whereas the period, remember, is in seconds. Now, if you don't know the frequency, we can still calculate the period, and we have two new equations to do that. The first one is for the period of a spring. Period of a spring is equal to 2 pi times the square root of m over k, all of that under the square root. So if you know the frequency with the mass in the spring, you can calculate the period using 1 divided by frequency. If you don't know the frequency, but you know the mass and the spring constant, then you can calculate the period of the spring this way. Remember, this little k here is your spring constant. For a pendulum, we have this capital TP for pendulum. It's a very similar equation. It's 2 pi times the square root of L over G, where L is the length of your pendulum and G is that gravitational constant, or 10. So here's some new equations for you to calculate the period of a spring and a pendulum. Now we're also going to, throughout this unit, we're going to apply some of the stuff we learned last semester. Okay, so you need to keep in mind a few things. One, remember acceleration is equal to net force over mass, Newton's second law. So we said there's some kind of restoring force. And we can actually calculate the acceleration, for example, of a mass on a spring at a given stretch. Because remember, Hooke's law was equal to force of a spring is equal to kx. So we could actually substitute this in for your net force for a mass on a spring. So it'd be kx divided by the mass. Okay, so remember some of those equations from last semester. You'll see those come up throughout this unit. We can also use conservation of energy. So looking at these two examples here, let's start with the pendulum. At this point right here, at this max height here, all your energy would be gravitational potential, UG. Okay, if I'm starting from rest. And then down here, if we call this height is equal to 0, all your energy is going to be kinetic energy. So we can use this gravitational potential energy equal to kinetic energy, and we can solve for how fast this thing is going at that bottom right here. Okay, so we will apply this conservation of energy as well as Newton's second law throughout this unit. Now, the last thing that we're going to kind of go over is graphically how to analyze an object that is in simple harmonic motion. So let's start out, let's use an example with the horizontal spring. So I'm going to kind of draw that out. And I'm not going to draw the spring because it gets kind of messy with drawing the spring so many times in here, but let's say at time is equal to 0 seconds. My horizontal spring is at this max stretch position. And then I let go, and after 0.1 seconds, it's right here. 0.2 seconds, it's right here. And then at 0.3 seconds, I'm at my equilibrium position. And what's going to happen after it passes that, it's going to start slowing down. So we'll draw right here, this is 0.4 seconds. Then we'll draw right here, 0.5. And we'll draw right here, this is 0.6 seconds. And then it's going to continue to repeat itself. It's going to move back and forth on this horizontal surface. So we're going to analyze this object, this mass on a spring, using a position time graph, velocity time graph, and acceleration time graph to kind of see what we end up with. And so let's start with a position time graph. So keyword there is position. So we're looking at the displacement of this mass on a spring. So let's draw there's position versus time. At 0 seconds, okay, I'm at that maximum, in this case would be negative position, so it'd be right here. And then at 0.3 seconds, we said we were at the equilibrium position. So let's go ahead and say this is 0.1, here's 0.2, here's 0.3. So that means we'd be right here at x equals 0. And then at 0.6 seconds, we were back at our full stretch position to the right. So 0.4, 0.5, 0.6. So we would be about right here. And then we're going to continue to repeat itself. And what we end up with is a graph that looks like this. And if you think back and remember back from your math class, from a geometry class, what we end up with is a cosine graph. So from a position versus time graph, your x is proportional to cosine Now let's look at a velocity time graph for this same situation. So let's draw our graph here. Now, again, this time it's the velocity. So let's go back up and look at this mass on a spring. Right here at time equals 0, you're at your maximum stretch. So your velocity is going to equal to 0. And over here at 0.6 seconds, again, your velocity is going to equal 0 because you're at your maximum stretch. So we can go on our velocity time graph and say, okay, this is velocity, this is time. We're going to start at 0, so we'll put a dot there. And let's go ahead and label this 0.1, 0.2, 0.3. We're going to be back at 0 right here. And at your 0.3 seconds, at that equilibrium position, we actually have our maximum velocity. So the V is the max here at your equilibrium position. And we'll kind of see why as we continue on throughout these notes in this unit. So how I would graph it on here is at 0.3 seconds, that's my maximum velocity. So I'd have a dot right up there. And if we just continue this, what we end up with is a graph like this. We're starting at 0, so this is a sine graph. So the velocity is proportional to sine t. The last graph we can look at is a acceleration versus time. So let's draw our graph out. Point 1, 4, 5, and 6. And this is going to be an acceleration versus time graph. Now let's go back up to our mass on a spring here. And at 0 seconds, our velocity was equal to 0 meters per second. A lot of times this is kind of difficult or hard for students to kind of wrap their mind around, but actually your acceleration is the maximum at this point. Remember, Newton's second law says acceleration is the net force over the mass. And in this case, it's going to be the spring, so kx over mass. So the larger the force, the larger the acceleration. And looking at this mass on a spring kind of situation here, you have your greatest stretch at this location. So that means you have your greatest force, which means you have your greatest acceleration. And same thing over here, this is going to be your max acceleration because you have the greatest force here. And at x naught, remember this is when you have your maximum velocity, but you're not stretched, so that means you have 0 acceleration. So your acceleration is equal to 0 at your equilibrium position. So knowing that, we can go over here, we could say we're starting with our maximum, in this case it'd be negative, because it was over there on the left side. And then at 0.3 seconds, we said our acceleration is 0, and at 0.6 seconds, we're back over here at the top. And if we continued this graph, it would look like this. Very similar to this position one here, so we would say that the acceleration is proportional to cosine time. So you do need to be able to kind of recognize these sine and cosine graphs and apply them to an object in simple harmonic motion. And one big takeaway here too is what we were talking about here. Okay, so this is sometimes difficult to kind of wrap your mind around, but you need to keep in mind at your maximum stretch, that's when your velocity is equal to 0, but you have your maximum acceleration. And at the equilibrium position, you have your maximum velocity, but your acceleration is equal to 0. So this should help with some of the kind of basics with an object in simple harmonic motion, and we'll start doing some more practice problems in class.